Hi everybody. I had a couple of questions about the problems in the practice of part one for the final. So I thought I would just run through all of them real quickly so you could check answers. The last video this semester kind of chokes me up a little bit, but I'll get over it. I'll try not to cry on my iPad. Here we go. So the first one is a derivative of a log, and so this is a question about the chain rule. Remember that we had couple of versions of the chain rule depending on what our original function looked like. So the version of the chain rule you were using here is the derivative of the log of something, and the rule for that was it's just 1 over the something times the derivative of the something, right? So all of our chain rule examples ended with times the derivative of whatever was inside. So we had basically 3 versions of the chain rule, one for logs, one for exponential functions, and one for powers. So this one's obviously logs, so this will be 1 over whatever mess is inside the logarithm there. So that's all of this stuff, which seems needlessly messy. Sorry, that's a skipped the t, so t plus 1. So 1 over exactly what's inside, if you can copy that down, times the derivative of what's inside. So my apologies for my t's looking like plus signs. Plus t plus 1 derivative. And so the derivative of this should be easy, and since it's 1 over something times that, often we just write that as one big fraction. So the denominator is certainly this thing, and then the numerator is going to be this derivative. So derivative of 2t cubed is 6t squared, the derivative of 4t is 8t, and the derivative of t is 1. So that'll be the answer to number 1. Number 2, we're trying to find the partial derivative with respect to x. And so that means we want to envision this function as a function of x. Now, my cheating way of doing this is to rewrite it so that the x appears the way we like x's to appear in derivative problems. What we like x's to do is to be sort of by themselves with their power with a number in front. So, for example, if I want to take the derivative of 7x cubed, that feels very normal. But if I want to take the derivative of x cubed times 7, even though that's the same thing, it just looks weird. So I would say that the first thing I want to do here is rewrite this so that the variable, the x, appears the way a variable should appear, which means that I would write that first expression as 3y to the 4th times x squared, because that means it looks like a number. Remember, we're treating the y as if it's just a number times the power of x. And similarly, the second term, this guy, I would think of that as 1 over y times e to the x, because again, treating this as a number, that just sort of stays where it is, and this has got the x in it. So in each case, I've got something that I'm treating as a number times something with just x, something I'm treating with a number times something that's just x. And if the variable in the integration was a y, I would think of it the other way around. But since it's an x, I want to think of it as a number times something with an x in it. So if I think of it that way, then when I take the derivative, I just leave the number part alone. So that y to the 4th doesn't change. And instead of in the original function, it's got times x squared. The derivative of x squared is 2x, right? Because that's got the variable in it. And then by the same idea, this 1 over y, this is just a number, so I leave it alone, and the derivative of e to the x is just e to the x. So this will be my partial derivative with respect to x. Notice I'm not simplifying these things because I don't have a calculator and I don't have to simplify it, so I'm not going to. So for number 3, you could do this either with the product rule or you could FOIL. To multiply this out, you could FOIL it, and then you don't have to use the product rule. So either way, I'll do it with the product rule, since that's something that you should probably know anyway. So just as a review, the derivative here is the first thing times the derivative of the second plus the second thing times the derivative of the first. And so to find out what that is, I just need to do those two derivatives. So the derivative of x squared minus 3 is 2x, and the derivative of x to the minus 3 plus 4 is negative 3x to the minus 4. So I'm just using my power rule in each case, and I should just stop there. We do not have to simplify, so why would you? So there's your answer. Number 4 is getting at the quotient rule. That's kind of obvious. It looks like a quotient. So the derivative here, quotient rule says that it's the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. And so all I have to do is those two derivatives. The derivative of x is 1, and the derivative of x squared plus 1 is 2x. And so that will be my derivative, and I don't even have to multiply by 1. No simplifying needed. The second part of the exam will be problems that are similar to the ones that we had on the 3 tests that are not these straightforward computational things. In other words, the second part of the exam is really meant to show that you know what these things mean and how they can be used to solve problems. So all in all, the final exam really does look like the test that you've taken. It's just that these computational problems from the test you've taken are on their own separate page without a calculator. But other than that, the exam looks just like your test. The exam is about 1.5 of your tests long. It fits on 3 printed pages front and back, whereas the other exams fit on 2 printed pages front and back. Okay, that's all I can think to tell you. Hope this helps, and I'll see you guys in the morning. Okay, on the next page, we have a simple max-min problem. This is to make sure that you can do the process, even without a calculator that can draw the picture for you. The process is, step 1, find the derivative. So in this case, it's 2x minus 4. Step 2, figure out your critical points, which means solving where 2x minus 4 is either 0 or undefined. So the only way it could be 0 is if x equals 2. Double check that that really is in the interval you care about. You really don't care about any x's that aren't between 0 and 3, so this one is okay. And then 3, just check the y-coordinates. So the y-coordinates are going to come from f of 2. That's my critical value. I also need to check f of 0, since that's one of my endpoints. And I also need to check f of 3, since that's my other endpoint. So I'm finding my critical points that are on my interval. I'm throwing that in with my 2 endpoints, and I'm going to just calculate, of those points, I'm going to calculate all the y-coordinates, and the biggest one is my max, the smallest one is my min. So if I do that, f of 2 is -3, looks like, f of 0 is 1, and f of 3 is, oh god, what is it, 9 squared minus 12, -3 plus 1, -2. Okay, so numbers aren't too bad. This is the smallest, and this is the biggest. The problem does ask us to give this as coordinates, so instead of saying f of 2 equals -3, I would say that's the point to -3. And instead of saying f of 0 equals 1, I'd say that's the point 0, 1. So there's my absolute minimum, there's my absolute maximum. Finally, we're down to the last 3 problems, which are all integration problems. The first one is a substitution, so let's do that. Remember, this is we're going to trade in the x squared plus 1 and use u instead. That's clearly going to make our integral look a little nicer. But I also have to throw in the derivative information. So I'm going to take the derivative of u, that's obviously just 2x, and I'm not going to leave it like that. I'm using this du over dx notation on purpose because du's and dx's are part of integrals, and the du dx notation then allows me to rewrite that derivative as du equals 2x dx. So we're really just treating this like a fraction, and we're moving this dx over to the other side. So the 2 things I put in the box here, those are 2 equals for equals that I'm allowed to do. So in my original integral, the denominator has a square root of x squared plus 1, so I'm allowed to make that square root of u, because I'm using this fact. X squared plus 1 can be changed into a u. That leaves me with this part, an x times a dx, which is not quite what I have a substitution instance for. I have this instead. So I think wishfully, oh, if this only were 2x d of x, I could do something. And I say, well, I could make it 2x d of x by just sticking a 2 in there. stick a 2 in. Now that does change the problem. I added a 2 in there as a multiplication. That's 2 times x. And so if I add a factor of 2 multiplied, I can offset that by adding a factor of 1/2 somewhere else. So now that really is equal to the original. I've multiplied by 2 and I've multiplied by 1/2, and so essentially I've multiplied by just 1. But the advantage of that is that now, here in the numerator, I see exactly what my substitution instance says. So I can change 2x dx into du. So I have 1/2 the integral du over the square root of u. Now that's entirely in terms of u, and so I should be able to do that antiderivative. This is one that requires that we rewrite the integrand. Instead of a square root of u, we wanted to get as u to the 1/2, and we don't like powers in the denominator. We would much rather have those as negative powers. And so a 1/2 power in the denominator is the same as a negative 1/2 power. So this is all the same thing, but now we can just use our normal power rule. The 1/2 is still there. This 1/2 doesn't go anywhere. And the power rule says I need to bump up this power by 1, which will make it a positive 1/2, and then I need to multiply by the reciprocal of that new power, which is 2. And of course I have a plus c stuck out there that I can't fit on the screen. And so the answer, the 1/2 times 2, goes away, and so I end up with just u to the 1/2 plus a constant. In polite company, we like to give the answer in terms of the same variable as the question. So the question had an x in it, so I'd much rather this not have some made-up variable. And remember, u is x squared plus 1, so I can just make that change. So instead of u to the 1/2, this is x squared plus 1 to the 1/2 plus c. Okay. The second problem, this is just using our antiderivative rule for e to the something x. And so that rule is, so e to the 0.2x dx. So antiderivative of e to a number times x is that same exact thing, but times the reciprocal of that, the number that's with the power there. If you think about it, when you take the derivative of this, the derivative of this guy is going to be e to the 0.2x, and then this 0.2 is going to be multiplied because of the chain rule. The real rule is it's e to the 0.2x times 0.2. So we leave this out here so that when the 0.2 comes out from the derivative, it hits this and goes away. Anyway, so that's the rule. So we have a multiplication by the reciprocal here for the antiderivative. That gets evaluated from -3 to 0. And so that is 1 over 0.2 is 5, by the way. So that's not a hard number, but you can just leave it like that if you want to. So I have 5 e to the 0 minus 5 e to the negative 0.6. If I plug in plugging in 0 for x, I get this. That's a 0. And if I plug in -3 for x, I get this. So again, we don't have to simplify anything. That's perfectly fine for the answer. And you can even leave the 1 over 0.2 there. I don't care. But in this case, 5 is a lot easier to write. And then finally, we have this last antiderivative, and this is, again, just getting at our basic rules. So I have the 1.5 just sitting there. And then what I like to do is give myself some space and think about what's the antiderivative of this guy. So I need to bump up this power by 1, which makes it 0.5, and then multiply by the reciprocal of 0.5, which is 2. Right? You could write 1 over 0.5 there if you want to. It's fine. But that's my that's my antiderivative of 1.5 x to the minus 0.5 is this guy. And again, don't have to simplify it. Plus the antiderivative of 1 over x, that's the one place where the power rule doesn't work. The antiderivative of 1 over x is just log of x, and then plus a constant. So as simplified or not simplified as you would like. So that's it. Those are the answers or solutions to the 8 problems that you have. This is the part of the exam that you'll have to take without a calculator, which means that you do not have to rewrite anything. You can just leave things as they come to your brain. So no need to do arithmetic or algebra of any kind for the answers to these problems.